Swayam Prabha. Digital India. Educated India.
Because I wanted to show you a French experiment with different branches, which I discussed already, can be explained by some different ways, and one of ways is just to look for the Fourier transform, and this is maybe the simplest, and you can find what is the leading frequency. But remember that if you have large amplitude of response, it is not a circular like harmonic shape, but it is a little bit more complicated, and this is visible on their findings. You see that this is the non-resonant solution. This is the resonant solution, but of a large amplitude, and you have such large amplitude that you can pass through the potential barrier, because these pluses are just minima, and this is called this picture is called the phase pulse rate. However, we have some more than only phase pulse rate, because there is a point which is stroboscopic point. You see the black point here, and there is also black point somewhere here. This is possible to see some points, and this is only 1 point. So 1 point means that there is response has the same frequency as the input signal. So input signal has some characteristic frequency, and the same frequency of the same period is for the response. In the next branches, you see that there are 2 points. 2 points. So this is subharmonic 2, and this is subharmonic 3. So 3 points, and this is a large orbit. So you can see large orbit, but for more pulsations, you have 2 pulsations which are marked by the Poincare points, but only 1 circle in the response. So this is the signaling that during the response there was some accumulation of energy from the pulsations, and here you have 4 black points. So these are called Poincare points, and you have 5, maybe here 5 points. 5 points. So this is interesting, but you can find the periodicity. You can identify periodicity on the phase portrait, and this is with the Poincare points, or by Fourier transform. So this is my comment to the story, because you see that this is like a resonant, non-resonant of a small with a period 1, and this is like 2 periods, and this is called subharmonic 2 by French group, and this is subharmonic 3, subharmonic 4, subharmonic 5, and here you have the branches. So these branches are going beyond the single frequency. You see, but this is like a broadband effect. It's a broadband effect. So when I should also tell how this was prepared, how this diagram with branches was prepared by us. So we took this is not a continuation, but it is the voltage output. This is the voltage output, which is estimated for random initial conditions, and finally we used only we noticed that only if we change only the velocity, like random velocity, and we can put the initial condition of a displacement in one of the equilibrium points, or in telling that this is the left equilibrium point, the negative one, and we select the random velocity. Velocity is telling that we could have different energy level because kinetic energy could be related with velocity. So initial velocity is telling that we start from different energy points, the zero potential, minimum potential, but velocity is could be any value with some interval. And then you can find different solutions. You see that simultaneously we have solutions present in different branches. Here. The first mode, yeah. So this is the first mode, but the first mode, so meaning that the curvature of this beam is the same. It's not the same, but it is the same sign. It's not changing like this. Yeah. So it's not changing. It's changing like it's only first mode. It's only first mode. So the shape is the same. However, the time is different. So it is faster or slower. Yeah, it's faster or slower. And it is important just to know that if we have a periodic excitation, we could be in phase of with a beam because I told you that there is some problem with periodic excitation. That there is one phase that you add energy in, and in the other phase you can remove the energy, and you can synchronize the motion of a beam. But this is the motion is only for the excitation. It's not removing the energy. Yeah, could be that the force could be negative or positive. Yeah, so it could be against the motion or in the direction of motion. The forcing could be of different sign, and sometimes you can observe that the balance of a force is higher if you have different periodicity in the output with respect to the input of the beam. Yeah. This is interesting point. Thank you for this question. Yeah. So this was the Fourier transform was calculated here. So now I stopped on that paper, and this paper was in fact devoted to magnetostriction. So this was magnetostrictive material. And yesterday you learned about this magnetostrictive. I would add to the yesterday explanation, but this magnetostrictive material is quite expensive with respect to the piezoelectric. However, it is possible to make some experiments. Maybe for application it is too expensive, and you put additional coil along the beam. Yeah, so the beam is magnetostrictive, and during the deformation, it is changing magnetization. Magnetization of the beam is changed, and there would be some additional effect of the magnetic field, and some of the magnetic field is present also in these magnets, but these magnets are placed here just to have the destabilization of the horizontal position of the beam. So you have some additional barrier to equilibria, like before, and the difference to the previous system is that you have some additional spring. You have additional spring because the excitation is to the basement, and the frame is connected with the base of excitation by some spring. Yeah, it could be also damper here, but here it is it was assumed that this is like a spring. And the authors thought that in such configuration you can have some amplification mechanism for energy harvesting. So this was called displacement amplification mechanism in such way. Yeah, and this system is also related to some other systems discussed in the literature, and these are called nonlinear energy sink. So nonlinear energy sink, you can find the nonlinear energy sink in some way that you want to dump the structure. So there is a very basic structure. Is you can think for the moment, you can think that this is the basic structure. The frame is a basic structure, and you want to dump the basic structure by some additional element, and this is nonlinear system. So you want to direct the energy to this small device, which is placed in somewhere in the structure, in the original structure. So the idea is different, because you in the nonlinear energy sink you have the structure and you add some nonlinear device just to accumulate the energy, and this is used in aerospace, for example, such a nonlinear energy sink, or maybe for the earthquake. Yeah, for the earthquake, you can also use some energy nonlinear sink. But here it is different concept. The concept is that we start from this device and we extend the device by additional spring, and we want to have some similar effect, like a direction of energy, but the energy is directed to this exactly to this end, to this resonator, which could be the resonance. However, we have originally we have this part, and we extend by the spring, and this was checked, but it is also working in some range of a frequency band. It is efficient. So it is efficient mechanism in some, and I would tell, but this is also some interesting point which was discussed maybe yesterday, but you can enlarge the frequency band by adding more degrees of freedom because there is evidently one more degree of freedom, but it is non-linear system. We talked about linear systems, but it could be even for linear systems. It is good to have more degrees of freedom when we have two resonances. So it could be that this is also interesting approach, especially when this is working. And here the authors are telling that. But you can have amplification mechanism. So without amplification mechanism is a red curve, and with the amplification mechanism is a blue curve. So you see that the blue curve is better than red one. Yeah. So this is I think it's an experimental result by the same authors. Yeah. And here this is with respect to what was told by Professor Grajan. So it is the system with some bias magnetic field and without bias magnetic field and with bias magnetic field. Means that if we have some magnetostrictive system, it is better to shift the or maybe to fix the working area with some non-zero magnetic field. It is not oscillating around zero, but it's some with some non-zero magnetic fields. Yeah, so you have some extra magnetization, but on the top of some non-zero value of a magnetic field. So you put some additional external magnetic field, and this is some bias. It is good to have some bias, but this is the effect which is coming from materials. But for some piezoelectric systems, you can this is not so important. However, this is also done by some robust effect of initial polarization of piezoelectrics, and here you have such a system that you have some additional magnetic field, external magnetic field, then you have some preferred magnetization, and there is some relaxation effect. But if you remove, if you change the if you add some stress, you change magnetization. But this magnetization can be moved to the original after removing the stress. So this is something understandable. But this is good effect with bias magnetic field. It's that one. The blue curve. Yeah. So they discussed also such effect. This was another paper in the same direction. So this was also electromagnetic system. You see, but it looks like to be larger system electromagnetic. Even the size of magnets is considerable. Yeah, with respect to the system, the coil and so on. So you have the coil which is moving. Yeah. And it is attached to the mass. The mass is coming with some springs which could be stressed in the on the way. So if mass is moving up and down, there would be some effect of the stress on these springs. So the potential energy would be higher, and there would be some barrier, but the mass is not preferred to be in the line with the springs. Yeah. So this is like a maximum of the potential energy, which is telling that there is a barrier. So this is bistable potential with some additional suspension, and they studied similar effect. So this was the potential of the study, and here they have results in their system. This is with this displacement amplification mechanism. So they applied additional spring suspension. This is called displacement amplification mechanism, and this is without displacement amplification mechanism. So it was helpful for the system to have some additional spring, and this is interesting. But I told you that this is not a surprise, because we think that if we enlarge the number of degrees of freedom or something like that, we manipulate with such effects. We can expect that there would be some help of the energy harvesting. And we also studied some system in 2023, but you know that time we studied with piezoelectric, because the previous papers were magnetostrictive and also electromagnetic. So we decided that we can use the original system, which was one air tube, and which was suspended additionally on some spring and damper, and we excited that system, and we obtained some nice results, telling that this is also useful procedure. So this was presented here. Yeah, so we had different levels of excitation, and this is unfortunately this is the scale is logarithmic scale. Yeah, so this is logarithmic scale, but your maximum is somewhere close to all the curves for each have different each colors. We have different excitation levels and with excitation amplitudes. So some cases are just marked here for the red curve. You see, but to just to show the time series of the response. Yeah. So we have parameters used to the system here, and the time series you can see the time series are just for the middle curve, the red one curve, and what can told that you have large amplitude of excitation when your nonlinear effects are more observable. Yeah. So you can hear the power is the highest just in some region, and we also studied the stiffness of the amplificator. The stiffness of the amplificator. It is interesting that there are two possibilities. For example, that if there is a very stiff amplificator, so this is actually rigid. So it is like the previous system by Inman and Ertug. And the other limit is that this is very flexible. And we studied with the system which is original system with respect to the stiffness of this amplificator. So you see that this is the small stiffness and this is the large stiffness. So the large stiffness there is an effect which was already in the Ertug paper, and if you have some intermediate stiffness, then you have some increase of the performance. So it is telling that some intermediate stiffness maybe is useful for the system to get better performance. And here there are some 3 points which we described. What is the here there is a phase portrait, and here there is a Fourier transform. You see that if you have complicated phase portrait, then you have many different harmonics inside. So this seems to be a very complicated motion. Maybe this is, I'm not sure. We can look more carefully because there is no continuous band. If we have some continuous distribution of the frequencies, we can tell about chaotic solution. But these are still some individual peaks. So it could be that this is still a multi-frequency response, but not chaotic. Chaotic is that you have some band. So not just individual peaks.
So can we tell that response is quasi-periodic?
Quasi-periodic could be possible. However, you see that the problem is that we have so many peaks. But quasi-periodic is that you have, for example, you can have two peaks, but if you divide one by the other, it is non-rational number. Yeah. So it's different definition. But here you have more periodics, more harmonics. Yeah. So multiple period response. Yeah. If you look here, it seems to be like a periodic, but very complicated. Yeah, a very complicated periodic with some modulations. Yeah, so this voltage. However, this displacement. So the displacement is also seems to be periodic. Yeah. maybe quasi-periodic, but we need, for quasi-periodic, we need to calculate what is the frequency with respect to the other frequency. So the ratio should be rational or non-rational, but rational, usually if it is rational, it is exactly rational, like 1/3 or maybe 2/3 or something like that. Yeah. So we can tell that this is close to the rational, but it's not. It's not so. Sometimes it is not so easy to decide with only with frequencies. This is the amplification factor. The amplification factor is interestingly, but the amplification factor was even here was the largest for the small oscillation. Yeah. This is the excitation, for small level of excitation, and maybe this is the amplification. It's a little bit improved. It is improving the even smaller oscillation level. Yeah. So it could be useful even for small oscillations. But here it is the solution. I told you that the large amplitude nonlinear could be could have some leading frequency like excitation frequency, but the second peak is appearing, and the second peak is much smaller. However, it is deformation from the circle. It's not circular response in terms of a phase portrait. So telling that there are some nonlinear effects inside this time series. Time series like this is x displacement against the velocity. The velocity against displacement. And we studied this effect. This is effect together with Abhijit Kiri. So he was working here with the group, but this is we applied some additional shape memory elements. Shape memory elements. The shape memory element is could be useful. Yesterday we heard about some stories about these intelligent materials, and but we need to prepare this in special way. Because the rest is very similar, but we only put some kind of shape memory element, which is here. So the paper is in preparation. So we have results, but it is not published. So we have shape memory element, and this is a coupling between the basement to the frame. And the harvester is inside the frame. So this was the case. And I mean that shape memory element can be also used to store some energy. So this is an interesting effect that you can have such a extra energy which is stored in some phase, and if you have a phase transition, then maybe you have some extra elongation or extra contraction. so this is quite nice effect, because usually such a effect of extra elongation or contraction is possible, but you need some more volume, more length. But you can concentrate that oscillator in a smaller size, but you have some element which is adding and some length and displacement. Yeah. So we have some kind of a loop, which is hysteretic loop for the material which we applied, and this is the potential, which is like a bistable potential for energy harvester. the restore force. I told you restore force is for exactly for this potential. And this is for the oscillator inside the frame. And the shape memory alloy spring is such a spring where you have distributed stress. So stress is distributed in some way. It is important to be aware of these effects if you design such a system, and you know that with stress that you can have partial transition. Of course, you need to prepare shape memory material in some with some components. You can control the transition temperature. So you select the material just to control the transition temperature, as Professor Aukarajan told that for the medical applications, you are with respect to the human temperature. So this is also it is not always like that, because for some other applications you can get shape memory alloy with respect to the room temperature, for example, or some other temperature could be done when the composition of the material is slightly different, but you can use such a spring. But also in the spring, during the work, there could be some partial transition, because it is the transition is happening. So this is phase transition for the shape memory alloy. Is there are two phases, like austenite and martensite phase, and these two phases are just different with the length, but also you can train your system for some memory to keep some memory the shape. But in our case, the most important is effect of the length, but it could be different length. So you could have extra length from the phase transition if you have some stress. Yeah.
Like we are using this shape memory alloy with respect like temperature changing the shape alloy.
There is no the temperature is room temperature. So if the room temperature is present, then you are sensitive to the very much sensitive to the stress. So you can get phase transition just because of the stress.
But it is like a slow process, like shape memory alloy. If you are just changing the temperature, it is take time to change the temperature. So
The temperature is another effect. Yeah. So you can. I think, but we also have some small change of the temperature in our system. But we have. If you look here, there is also hysteresis for the same temperature, which is I have another answer, because if you have constant temperature, then the phase change could be with respect to the stress. And this is the diagram. This is the displacement and force. So you have also such a diagram with hysteresis, force and displacement. But there is some change, or the change of temperature is also happening. However, you needn't to increase the temperature just to have the critical value, because the critical value, critical temperature is defined for the sample with no stress. But if you provide some stress, then also temperature is changing. Yeah. So this is you are right, but there are three components. but it would be that if you provide stress, when the critical temperature is also changed.
It is a phase change like temperature.
These two effects are important, for shape memory. you can have also some hysteresis with the temperature. So, but I mean, but this is the there is a distribution of stress. Stress maximum is on the surface. And, inside there is stress zero. So this is somehow possible to get such a distribution. So we are just telling on this picture, but the stress is not uniform inside the spring line. And we've got some solutions like that. So the solutions still need to be, and the temperature is kept constant. You see that it is constant. But you know the constant temperature. This is assumption for the calculation. That the temperature is constant, but there would be some small fluctuation if you have a phase transition in both directions. There could be some kind of a small fluctuation of temperature. So in the experiment we are going to perform also the experiments. We will check what would be the temperature. But it would be for sure there would be some fluctuation in temperature. But in the calculation you can keep constant. Temperature. And we also used we also get some similar solutions. This is like with respect to the spring, and this is the spring, which is shape memory alloy spring, and there is one component which is a linear component of a spring, and I will explain you what is the linear component. So we change the linear component of a spring, which is on this graph. It's an inclination of this force and displacement. Inclination of this force and displacement can be fixed, and when we can again look for some dependence for the very steep and very flexible system, and we can find that this amplifier is also useful for some intermediate range of a stiffness. And moreover, we can conclude this is like initial stiffness is that one. So the different stiffness. So we also show different stiffness. We can conclude that there is some more information. Some more energy can be applied, or maybe can be stored in the shape memory alloy. It's not only the spring, but it's also some kind of store of energy. So the energy could be released for some larger displacement. And this effect is called superelasticity. That you don't change the superelasticity, but you have the stress of the same level, but you can change the displacement, or deformation. You can deform more, but you still have the same level of stress. And this is the effect of a shape memory alloy, and you see that this could be useful for our system, because we can have some more displacement even if stress is not increasing. We found also some very complex solutions in this system. But this very complex solution, this is maybe chaotic. This is maybe chaotic because I see that this is no regularity here. But a chaotic solution could be present because, as you remember, Professor Sheikh Farouk told you that in the linear system you can add solutions. You can add one solution to the other solution, and this is also a solution. And in non-linear systems, you can also add solutions, but the result of adding of this summing would be different. It could be that some part of a final response would be similar to the first solution, and some of them would be like the other solution. So this is like a mixture of solutions. So the response would be like not like a mathematical sum of two solutions, but a mixture of these two solutions. And the mixture of two solutions would be like a chaotic mixture. So this is because there are more. So in other words, the chaotic solution could be also thought like a solution which is result of multiple solutions present in the system, and they compete in this chaotic solution. You can find that there are some also some leading frequencies, but the distribution in terms of frequency is like a band distribution. It's not individual frequency, but it's more like band distribution. Yeah, so we had different stiffness. You see that these are examples with different stiffnesses. And with respect to our first paper, where we had normal spring, these are three different periodic, and this is chaotic, and this multi-periodic, but it's irregular. It's multi-periodic but regular, and this is chaotic. So sometimes it is small amplitude oscillation, sometimes it's large amplitude oscillation, and this is also called intermittence. But you switch, and suddenly you have some interval of the completely different solution, but you go back after some period. You go back to larger oscillation. And this is multi-periodic, but it is still regular. Some regular resolution. And then I had also some papers which we are still working in preparation about synchronization. I told you synchronization was maybe the last topic. So I would be very quick now. And there was a question: what is the best, potential barrier? And I would tell that the potential barrier it is like a compromise, because the potential barrier is not it's not going to be very useful if we have a small excitation, but it is making the amplitude larger. So we can lower the potential barrier to zero even when we have a flat potential, and this is quasi-zero stiffness. This is called quasi-zero stiffness. So we have a potential which is given by higher order powers. It is not a parabol, but it's like x to the larger to 4 maybe. So in a small displacement, relatively small displacement, you can think for parabol, the original parabol, if we have no any scaling inside, then one is like a interesting point, but you could have parabol which is and if x is larger than 1, then you have you have effective enlargement of the value by the power, but if it is smaller than one, you go down and you have some flattening of the potential, and this one is it's only we need to decide because the one would be dependent on the size of the system and on some selection of the materials. So we need to like stiffness. So we can adjust one to our units. For example, if we want to have one could be like 1 meter or it could be like 1 centimeter. So, but this is dependent on the size and the materials inside. So we can plan this in such way. We can plan that the potential is possible to have a very flat, but inside there would be like a free motion and barriers on the sides. Here we have such two oscillators coupled, but they have quasi-zero, and we studied some so you can see this flattening effect. The flattening effect is here, and we also studied here the bifurcation diagrams. These are energy harvesting systems. This is energy harvest. We have like current here. This electrical circuit, and when the bifurcation diagrams are present, and we have also these branches of solutions for many systems, but we can look for synchronization, and the synchronization I would tell that for this synchronization, maybe which are recurrence plots, are good for to measure the synchronization effects. So I would tell you that if the system is well synchronized, for example here, you have the diagonal lines, and if it is not so well synchronized, so these are some other patterns, and you can look for the statistics. So recurrences are looking for statistics. The recurrence plot is calculated, but you compare the state in one time, and this is like x and y are times, but could be different times. Exactly in the middle you have the same time, because the time 1 is equal to time 2, and you have a time series. Could be the same time series, but it is like a cross recurrence, right? So 2 different time series. So this is you compare the time of these are very identical. So you think that you mean that this is they are going exactly the same way. These recurrences could be used as a tool to study synchronization, and I would tell that the oscillators could be slightly different, but for nonlinear systems it is not a very big change, because synchronization region is enlarged for this is the nonlinear effect, one of the nonlinear effects, but we have similarly to the resonance. Resonance region is enlarged, and also synchronization region would be enlarged. So I think that I can maybe I can finish on that, because I was prepared only also for some next points with enlarging the number of oscillators. But maybe this is too much, so I would finish on that system. So maybe you have some questions. Any questions? No questions. Yeah, I would tell, but with synchronization. I mean, but this is you can think about resonance also as a synchronization because you have the this is the synchronization of your oscillator and the signal which is the input signal. Yeah, so you can think about some synchronization. So synchronization here you can treat you have two oscillators. You can treat that this is like one oscillator is synchronized with the other. However, in this system it is a little bit more complicated because looked more carefully, both oscillators are excited by the same input signal. So you can tell that such a complex phenomenon, but you have to the original. These are and the frame is excited. So each of the oscillator is excited by some inertia. However, they also interact with each other, and you have some effect of coupling. Yeah. So, for example, it could be important if you have slightly different parameters, and you could have some tendency of subharmonic solution in one oscillator, and the second is non-resonant, but because of a coupling, you can synchronize these two to one of these